higher order linear constant coefficient non-homogeneous differential equation. Last day I have already discussed details about the linear constant coefficient differential equation. Now today we consider the case f d y is equal to qx, where qx is equal to e to the power mx and f of m is equal to 0. But f of m not equal to 0, we already have discussed. Now if fd, we know fd is a polynomial function of d. So if f of m is equal to 0, so this polynomial must have a linear factor like d minus m. So we can write this polynomial as d minus m to the power r, d minus alpha 1, d minus alpha 2 up to t minus alpha k. Now d minus, now d of e to the power mx is equal to m e to the power mx. So d minus m e to the power mx is equal to 0. So if we take the inverse of this operator d minus m from both sides, then we get e to the power mx is equal to inverse of d minus m on 0. So this is 0. So e to the power mx is equal to 0. It is impossible. So we cannot take in this way. So we need to take and we need to follow another technique. So how can we solve d minus, find out the particular integral of this case, this differential equation when fm is equal to 0. So now we calculate d minus m y is equal to e to the power mx. We know for this differential equation how can I find the complementary function. Now we are interested to find only the particular integral. Now this differential equation can be written as or dy dx minus my is equal to e to the power mx. It is a simple first order linear differential equation. So we need to multiply both sides by e to the power minus mx. So e to the power minus mx dy dx m e to the power minus mxy is equal to e to the power mx, or we know that after integration we get y e to the power minus, here whenever we multiply with this left side by e to the power mx, so we need to multiply right side by e to the power minus mx. So we get at right side we get 1. So after integrating we get y e to the power mx is equal to, the integration of 1 is equal to x. There is another arbitrary constant, but since we are interested to find the particular integral, so we avoid the arbitrary constant. So we get y is equal to x e to the power mx. So this is the particular integral for this differential equation. Now d minus m square of y is equal to e to the power mx. If we put d minus m y is equal to u, so we get d minus m of u is equal to e to the power mx. For this differential equation, we know that the particular integral is obtained as u is equal to x e to the power mx. So from this relation, from this equations, we get d minus m of y is equal to x e to the power mx. Now for this differential equation, we get dy dx minus my is equal to x e to the power mx. Now we need to multiply both sides by e to the power minus mx and e to the power minus mx. So ultimately we get the right side only x, and integrating finally we get y is equal to e to the power minus mx into e to the power minus mx into x square divided by 2. We also avoid the arbitrary constant. So finally we get x square, y is equal to x square by 2 e to the power mx. So for this case, the particular integral obtained as y is equal to x square by 2 e to the power mx. Y is equal to x square by 2 e to the power mx. So in the same way, if we calculate, then for d minus m to the power r y is equal to e to the power mx, we get the particular integral like this, x to the power r by factorial r e to the power mx. Now we just saw a particular case. If suppose d minus alpha of y is equal to e to the power mx. So for this case, we get the particular integral like this, y is equal to the particular integral, this is the particular integral, right? Particular integral is equal to 1 by d minus alpha of e to the power mx. So this is 1 by d minus alpha of e to the power mx. Now here for this function it is not equal to 0, so and the denominator is not equal to 0, so we can put here d is equal to m. So we get this is m minus alpha. So if we take this 1 by m minus alpha, it is a constant, so we can take it outside. So we get m minus alpha of 1 by d minus m of e to the power mx. Now, so for this reason, we get the solution as m minus alpha x e to the power mx. In this way, if we get the solution as for same technique, in similar way, we get the particular integral for this equation as 1 by 1 minute x to the power r by factorial r into 1 by m minus alpha 1, m minus alpha 2 up to m minus alpha n into e to the power ns. So now I finish today's lecture.